Hello, everyone. Today, we're going to discuss the problems in the JWO finals this year. The JWO stand for the Junior Wiskunde Olympiad in Dutch. In English, it is the Junior Mathematical Olympiad. And JWO is a competition for the students in the year 3 and the year 4 in the Flemish school in north part of Belgium. And normally students have 3 hours to finish the competition, and there are only 4 problems. So it's regarded as the starting of the Olympiad competitions in Flemish schools. So normally it's not so difficult. And for this year, I think it's much easier than expected. Expectation is a little bit more difficult, but if I see the problems, it's quite easy. So we start with the first one. The first one, okay. The first question is something about combinatorics. Um, Below you have the translation. So in a m times n grid, so m row n column grid, rows draw a path through all the diagonals, through all the squares. And the target is that the path goes through each square once and only once. Yeah. So here we have a example of 3 times 4 grids. And we have to show that for any m times n grid, Ross is able to draw such a path. So it's very natural that we start with the simplest case. So if m is 1, so we start with m is 1. So 1 times n grid. So 1 row is there's only 1 row, for example. And for example, here we have 1, 2, 3, 4, 5, 6, 7. Maybe we have seven squares. So n is odd. So where n is odd, okay. So the path can start from the bottom left, and end with top right. So it starts from the bottom left and ends with top right. Okay. So when n is not odd but is even, so we have another square. So it's natural that it's end with bottom right instead, right? Start with the same start from bottom left, but end with the bottom right. So that's quite simple. Yeah. So now think about m rows. For m is n, for m is 1, it's easier. For m, if we have m rows, and we try to separate the cases into 3 subcases. So we have the case 1. Case 1 is when n is row odd. So when n is odd. So when n is odd. Because for n is odd, here we know that the path starts from bottom left and will end the top right. So it starts from bottom and will end with top. So that gives us a possibility that we can stack m and 1 times n grid, stack m and 1 times n grid into the grid. For example, start with 1 times n, and here is again the 1 times n, and dot 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 dot, and here at the end we have 1 times n. So we have m component like this. So sorry, here it should be 1 times n, 1 times n. So we start with the square on the bottom left, and we know when n is odd, it's always end with here, end with the top right, yeah? And then for the second stack, we can start with the bottom right and go this way. And we know because n is odd, it will end with right here is the bottom top. Yeah, the top left, sorry, the top left. And we can do it again. We can do such again, and it will end with a top right. So when n is odd, we always start with bottom and end with top, or we start with bottom and top. So the m component can be stacked, yeah, from bottom to top. So it's always start with bottom, end with top, and the top again is the bottom of the second component, and end with top of the second component, which is the bottom of the third component. So we have m components. So apparently, it will go in this way. So at the end, we can find the path. So it's end with here or here. It doesn't matter. It doesn't matter, but the path exists, right? So that is the easy case. Now, the second subcase is n is even, when n is even, right? And now we have to discuss when the parity of m. So when n is even, we cannot use this, case, right? So when n is even, so m is odd. When m is odd, so we have m times n, which is a grid of odd times even, right? And you can see it's exactly a reflection image of n times m. So we know m times n, which is even times odd grid. So even times odd grid, we have just discussed, which is the case one, So case one is m times when m is even and n is odd. So that's the path exists, right? Because we just proved that for any n, when n is odd, the path exists. So here, actually, n is odd because we just have a refraction of the grids makes the number of columns an odd number, and the number of rows is an even number. So the subcase 2 is just a refraction of subcase 1, right? So it stands for the subcase 2 is also possible. What about subcase 3? So subcase 3 is n is even and m is also even. So m is also even. So in this case, we didn't discuss before. So the even times even. So in this case, we can just divide. So the grid is even times even. So here we have m, here we have n. So in this case, we just leave the first column out. The first column, this one, as a component. So here we have m times 1 grid, m times 1 grid. And the rest part is m times m minus 1 grid, right? M minus 1 grid. And we know that now m minus 1 is odd. Yeah, m minus 1 is odd. So the n times m minus 1 has such a path because the number column is odd number. So such path exists. So if we start with this, and it will go into this way because it's odd, and then go again, again, and so on. Because m is even, so m is even, so the path in this grid will end up with the top left, will end up top left, because m is even. We have even number of such components in the stack. So it will start with the bottom left and end with the top left, right? And the rest, we think about the m times 1 grid is just also a reflection of 1 times n grid, because now m is a even number. So it's from the bottom to the bottom. So that means it will go this way and end up with the bottom, the same side, bottom and the bottom, right? Because it's a, a reflection of 1 times m. So we call it bottom to bottom. So actually it's the right and the right. So that is a proof that for the sub case 3, the path also exists. So or concluded for any case of m and n, for any cases about their parity, the path exists. Okay, so that's a proof of the problem number 1. Problem number 2 is relatively quite easy. So it's a geometrical one. So stands like it stated there is a right triangle ABC. So here we have a right angle C, where A and B are 2 legs and C is the hypotenuse. Point P lies on this half line BC such that BP is C, and the same Q lies on the half line of AC where AQ is C. And if QPA is also right angle, so QPA is also right angle, what is the ratio A over B? Yeah. So it's very straightforward because we know that BP is C. So then we have the PC is C minus A. Yeah, because BC is A, and the BP is C, right? And the same as AQ is C. So the QC is C minus B because AC is B, right? And notice that the angle ACP is also right angle because ACB is a right angle, so ACP is also right angle. So PC is the height on the hypotenuse in the triangle of QPA, where the angle P is right angle. So PC is the height on the hypotenuse. So we know that some theorem about that, but we can also show that the two triangles are similar. So the PCQ is similar with the ACP. So it's quite easy. I can skip it because we have a pair of two right angles the same, and we can easily show this angle is this angle or this angle is this angle, right? So that means the PC is a geometric mean of AC and QC. So here we have the PC, which is C minus A square equals AC. AC is C, AC is B, and QC is C minus B. And then just expand it. Q square minus 2AC plus A square is BC minus B square. And just note that A square plus B square is 6 square, where the Pythagorean theorems. So c squared equals to a squared plus b squared, right? And then we have two c squares. So sorry, I have to remove it somewhere, erase it. Okay. 2c squares minus 2ac equals to bc. So that is c equals to 2 so c equals to a, sorry, so 2c equals to a plus half b, right? And we just replace c with this into the Pythagorean theorem. So there we have a plus half b square is a square minus plus, no, plus b square. And expand it again. So we have ab a square plus ab plus b square divided 4 is a square plus b square. And just remove a square from both ends. And we have ab equals to 3 over 4 b squares. So that means a over b is 3 over 4. So that is the answer here. Okay, we go for problem number 3. So that is definition of a so-called self-describing number. So self-describing number is a natural number. It's a positive integer where the first digit indicates how many times the digit 0 occurs or appears in this number. And the second or the next digit, second digit, indicates how many times digit 1 occurs. And the third one indicates how many times the digit 2 occurs, and so on, and so on. Yeah. So, for example, 2020 is a self-describing number. Why? Because the first two stand for there are 2 zeros, yeah, 2 zeros. And the second 0 stands for there's 0 ones, yeah, indeed, no 1 appears. And the third digit 2 stands for there are 2 twos, yes, there are 2 twos. And the last one stands for the 0 threes. So 2020 is a self-describing number. And the problem asks us to find the smallest and the largest self-describing number. Okay, to solve this question, of course, we can try from some examples. But before that, as a solution, I want to start with two lemmas. The lemma 1. So lemma 1, we claim that the sum of the digits in a self-describing number is equal to the number of digits. For example, 2020, the sum of digits is 2 plus 0 plus 2 plus 0 is 4. And the number of digits, 2020 is a 4 digits number, right? 4 digit number. Why? Because this number is quite easy to prove because from this definition, each digit in the self-describing number stands for the number of appearance or a number of occurrence of different digits, right? So there's no overlapping. So if you add all the numbers, all the digits in this number, it must be the number of the digits. Yeah. So the lemma 1, so it's not lemma 2, so lemma 1 is easy to prove. Okay. The sum of the digits equals to the number of the digits. Okay. The lemma 2, we claim that The self-describing number consists at least 3 digits, at least 3 digits. And one of them is 0, and the two others are non-zero numbers, a non-zero. Okay, so that's our claim. We have to prove, yeah. So for all any numbers, any natural numbers, the first digits must be a non-zero. Yeah, let's say the first start with A, so A must be a non-zero unless it is 0. Unless it's a 0, but of course, a 0 is not a passive integer, right? So for any digits as a natural number, start with A, so A is non-zero. Yeah, so that stands for in the self-describing number, there must be a 0 digits, and there must be digit 0 because per the definition, the first digit stands for how many times the digit 0 occurs. So that means there must be 0 or zeros, yeah, or zeros, yeah, at least one, but can be more, right? And since A is non-zero, so that means in the order digits, that must be a position like A plus 1. A plus 1 digits, that is a non-zero. There is a non-zero. So if we have a table like the digit and value, or the value, for example. So if we have such table, so digit 1 is the first digit that we stand for A. A is non-zero. A is non-zero. And dot, 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 we don't know where. So it's A plus 1. The A plus 1 digits, so that must be a non-zero number. Must be a non-zero. Because from the first one, we know there must be zeros. So that means even before the A plus 1 or after the A plus 1 here, somewhere we should have 0. Yeah, somewhere we have a 0. So that means there must be at least 3 digits. One digit is 0, and the two others, which is A and A plus 1th place, the two numbers are non-zero. So that's the proof of lemma 2. Okay, so remember we have lemma 1. The sum of the digits is the number of digits. Lemma 2, the self-describing number consists of at least 3 digits. One of them is 1, two others are non-zero. Okay, now we're going to solve the first question for the smallest what is the smallest one of the self-describing numbers? And we know from lemma 1 or lemma 2, there are at least 3 digits. Yeah, at least 3 digits, because there are at least 3 digits. So from lemma 1, we know such number is at least 3 digits number. And that means if we have A, B, and C, okay, the 3 digits, A plus B plus C is 3 per lemma 1. And there's at least 1 0, A or B, not A, but B or C. B or C is 0 per the lemma 2. So there is only one possibilities, the C, which is 0, 1, 2. Such kind of combinations. So the 3 digits must be 0, 1, and 2. 0, 1, and 2. But in this case, we don't have any 2. So you see the combinations. We have 0, 1, 2. And we don't have a digit which appears twice. So that means there's no such self-describing numbers. So we can also try, for example, 102 or 120. They are all not self-describing numbers because there's no appearance of two, no appearance of twice, right? So this is not possible. So that means at least we'll have 4-digit numbers. 4-digit number as the smallest one of the self-describing numbers. Very similar. We have A plus B plus C plus D equals to 4. And BCD, where BCD, one of the BCD equals to 0, one of the BCD. So think about combinations. So we have 0, 0, 1, 3, yeah, for example, because here is the only possibility, because we don't have a 0, 0, 0, 4, because otherwise, yeah, we have at least 2 non-zeros, right? Remember lemma 2, at least 2 non-zeros, 1, 0, right? So that's a possible combination. Or we have 0, 0, 2, 2, or we have 0, 0, no, sorry, no more zeros, otherwise it makes no ends. So here is no 0, 0, 1, 1, and 2. So they are all the possibility regarding to the combinations of digits. And in this case, we have 1, 3, but we don't have any digits appears 3 times. So that is not possible, right? Because the 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 most appearance is digit 0. It appears twice. So we don't have any digits appears 3 times. So this is not possible. For this one, it's possible. And the non-zero start with non-zero, so A is 2. So it must be something like this. It's bigger than 2000. So actually, the 2020 is a self-describing number. 2020 is also bigger than 2000, right? It must start with 2, must start with a non-zero number. So it's at least 2000. And for the third one, we can form as start with 1. So it's 1, 0. Yes, stand for 1, 0. And 2 ones, 2 ones. Yes, we have 2 ones. And 1, 2, 1, 2. Yes, 1, 2. And 0 threes. So in this case, we can have a self-describing number, and the only one in this case is 1210. And this one's smaller than 2000. So that makes sense. The 1210 is the smallest self-describing number. Okay. Now think about the largest one. Think about our largest one. So we know for the decimal number system, yeah, we have at the most 10 digits. At the most 10 digits available. So per the definition of the self-describing number, it has at the most 10 digits. So we are aiming to find the largest one in the 10 digits, 10-digit numbers, okay? And we know that from lemma 2, there's at least 1 0, at least 1 0, and at least two non-zeros, right? So that means the number of zeros we have at the most 8 zeros. At the most 8 zeros, because we have 2 non-zeros, right? So the first number A is max A equals to 8. So we start with 8. So we have, if we start with 8, and it's natural that the number 8, the digit 8 is 1. Yeah, because we have 1 8. and the rest is 0. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Something like this. But unfortunately, we have only one. We have also 1, 1. So the second digit must be 1. So that brings us a contradiction. That is a contradiction. We cannot make this number a self-describing number because the second digit must be 1, right? So that is not possible. And if A is 7, so if we start with 7, because we know the sum of the digits, the sum of the digits of all the digits must be 10 because we have 10-digit numbers, right? So the sum of the digits must be 10. So we have 1, 7 already. So the sum of the rest must be 3. So we have such of combinations. We have 0, 0, dot, 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 0. So we have 7 zeros and 1 and 2 and 7. Yeah. So that is the only possibilities, right? Only possibility for the combinations because we have a 1, 7, and all the digits, the sum of all the digits must be 10. So there must be 1 and 2, which gives 1 and 2. 1 plus 2 is 3. You might ask why not 0 and 3? Because we have defined the zeros is 7. The number of zeros must be 7, right? So the 3 cannot be decomposed as 0 plus 3. It must be 1 plus 2. Yeah, so it must be 1 plus 2. And in this case, think about the appearance of 2. So we have 2. If we have 2, the digit 2 in the self-describing number, it means there must be one digit which appears twice. But no, we don't have it. We have a 0 which appears 7 times, and a 1 and 7, which appears only once. So there's no digit appears twice. So that is the contradiction. So we don't have any self-describing number from these combinations, right? Okay, case 3, if we start with 6, and similarly, the sum of digits still must be 10. That means the non-digits, the non-zero digits, if we sum them up, it will be 10. So the combination will be 0, 0, dot, 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 0. So we have 6 zeros and 1 6, and the rest must be 4, right? The rest sum of must be 4, and the rest are non-zero numbers. So that must be 1, 1, and 2. There's no other possibilities. No other possibilities. So we have zeros, 6 zeros, 1, 1, 2, 6. Is it possible to form a self-describing number? Yes, yes, because in this case, the 6 stands for 6 zeros. So we have start with 6. And how many ones there? There are 2 ones, right? There are 2 ones. So followed by 2. How many 2s are there? Only 1 2. Only 1 2 here. So and 1. And what about 3? No 3. No 4. No 5. How many 6? 1 6. No 7, no 8, and no 9. So that is the one number and the only one number in this combination stands. Yeah, so we prove that the largest self-describing number is such numbers that start with 6 and 2, 1, 3 zeros, 1, 3 zeros. Okay, that is end for problem number 3. Problem number 4. It's quite easy. It's quite easy. I don't think that's a good question for the level of the finals of JWO. Uh, it's, it is a kind of number theory questions, right? For each natural number n bigger than 0, we find the solutions x or y, where the x over x, 1 over x, sorry, plus 1 over y plus n over x over y is 1. And we have to prove that there's exactly one such solution if and only if n plus 1 is a prime number. Yeah. The first four, we just rearrange these equations. Rearrange equations by multiply x, y on the both ends, because x and y are non-zero. They are denominators. Because x, y are non-zero because they are denominators. So we can just multiply x, y on the both ends. It gives us y plus x plus n and equals to x, y. And just do some rearrangement, x, y minus x minus y equals to n. So the next step is the key to the answer. We try to factorize the left part. So we can have x minus 1 times y minus 1. So it gives exactly the first three terms as xy minus x, but plus 1. We don't have plus 1 on the left, so that means we have to plus 1 on the right as well. So we have such kind of equations. Yeah. And it is clear that x and y are part of integers. So that means x minus 1 and y minus 1 are also non-negative integers. Yeah, they're also integers, right? Okay, so it's easy to say if n plus 1 is prime, that means we can factorize the right part as 1 times n plus 1, right? Because x is no bigger than y, so it's easier that we get x minus 1 equals to 1, and the y minus 1 equals to, sorry for my writing here, eraser. Okay, so my y minus 1 is n plus 1. So it gives us a single solution, x2, and the y is n minus 2. Okay, so when n plus 1 is prime, the equation gives exactly only one solution, right? So we discussed when n plus 1 is composite. Yeah. If it's a composite, that means n plus 1 can also be written like p times q, where p and q is bigger than 1, and we can just assume p is no bigger than q without loss of generality. So that means in addition to this solution, we can have the second solution, at least x minus 1 is equals to p, and y minus 1 equals q, and which gives x is p plus 1, and the y is q plus 1. So that shows if n plus 1 is a composite, and the equation gives us at least two solutions. So altogether, if we combine these two cases, we have shown that if the equation gives only one and only one solution, and the condition is n plus 1 is a prime number. So that is the necessity and the sufficiency conditions. Okay, that ends for the problem number 4. So in general, I think these 4 questions are quite easy, and much easier than expected. And um, it's likely that the cutoff for the prizes will be also higher than expected. And the result will be announced in 10 days. So actually, we'll know, okay, what is cutoff of the prizes and who will get the prize in the Wednesday, I think on the Wednesday in the week next, and yeah, in the week after next week. Okay, thanks for your attendance, and let's see. Tomorrow we'll have also the explanation of the 4 questions, 4 problems from the final of WWO as a Flemish Mathematical Olympiad, and see you then again tomorrow. Bye bye.